All right. Well, good morning, afternoon, and evening, everybody. Thank you for joining me in this virtual conference today, and I hope your day is going well wherever you are. My name is Jim. I'm the co founder and CEO of a startup named Phaedra. Our mission is to make AI more accessible by building self serve software that helps other people build high impact AI solutions, and we focus exclusively on the industrial sector. More importantly, I'm here today to share with you some lessons learned and best practices that my co founders and I have gathered over the years on how to apply AI effectively to large physical real world systems. These lessons are shaped by real experience. Specifically, they come from our experience applying AI to many of Google's data centers while we were working at DeepMind. From our experience applying AI to optimize wind turbines, our experience working with electric grids, and many other areas where we've applied AI since. All of these applications, of course, involve large physical and usually mission critical infrastructure where safety and continuity of operations is paramount. Now, for the purposes of today's discussion, we'll start off first with an overview of why industrial systems need AI and advanced data analytics. We'll then ground the discussion in a real world application using Google's data centers as the working example. And finally, we'll cover the hard fought lessons learned from applying AI in the field. So, with all that being said, let's jump right in. So to set the stage, I wanted to touch briefly upon why industrial systems need AI and advanced data analytics more generally. Now, this may, already be common knowledge for many of you on the call, but the first thing to note about industrial systems is that they tend to be very large and complex, right? You have lots and lots of equipment in the field, and all of these equipment are connected and interacting with each other in highly nonlinear ways, and the sum of this nonlinearity is incredibly difficult to model from a first principles physics based perspective, and thus makes them very difficult to optimize. The second challenge with industrial systems is that they're incredibly dynamic, and because the current status quo relies upon hard coded rules and heuristics for these large industrial systems, these rules and heuristics are too brittle and they're not able to adapt to the incredible dynamism within these plants. You've got weather conditions that are changing. You've got business parameters and KPIs that are changing. You've got equipment that are changing or degrading. You've got people who are operating the system who are changing. Right? These are all various sources of dynamism within these industrial facilities. And finally, this is all, of course, underpinned by lots of data, right? A lot of these systems were automated since the 1970s to 1980s with the advent of digital controllers, right? In order to automate something, you, of course, first need to sensorize and collect data. So a lot of these systems already have been collecting lots of data. They may not be, the right quality of data, but the data does exist. And, the summation of these three areas makes AI particularly valuable within the industrial field. There are, of course, many, many use cases for AI here. But as we well know, there are major challenges, to apply AI. Right now, as many of you look on this slide, you'll recognize, I'm sure, many of these challenges, right? From having to work with a general lack of sensorization, right? To having to work with highly risk averse industries, right? To having to integrate with a lot of legacy control systems, etc. Right. The purpose of today's conversation is not to illustrate and discuss all the challenges, of which there are many, but rather to expound upon some best practices for how to deal with these challenges, right, in order to deliver high impact, effective AI solutions. Now, of course, we do need to ground this, right, in a real world example. So the first example that I want to chat with you about is around Google's data centers. Now, for context, what we did with Google's data centers is we created a fully automated AI control system to manage the data center cooling. As you can imagine, if you've ever walked into a data center, they're essentially extremely large warehouses the size of several football fields laid end on end, right? And they're stuffed with millions of servers inside of them that consume lots and lots of energy so that everyone can have their YouTube cat videos and their Google searches and their maps for navigation, etc. So the overhead associated with running a data center can be quite large. In order to keep the servers cool, you have these really enormous pieces of electrical and mechanical infrastructure whose job it is to take the enormous amount of heat that the data center generates and expel it to the outside environment. Now, these mechanical systems can be a very large portion of the total data center overhead. And what I'm about to show you here, right, is the system that we built while at Google and DeepMind in order to reduce Google's data center cooling energy consumption by approximately 40%. So this is a picture of one of the data centers, right, that we released many years ago. Now, most data centers will not look this clean nor colorful. So in that sense, I suppose it's Google specific. But what is not Google specific is a lot of the equipment that you see in this picture, which will be equipment that's commonly found in many industrial systems. So specifically, in this picture alone, you see a lot of chillers on the left-hand side. So those are the big, greenish-looking cylinders, green and black cylinders on the left. These chillers, of course, convert hot water into cold processed water that then goes back to the server floor. You've got a lot of pumps, both condenser water pumps and processed water pumps serving the system. You've got some heat exchangers in there. You've got a bunch of valves, right? A lot of moving liquids. And, outside of this particular mechanical hull, there are some cooling towers outside, that is expelling additional heat to the outside environment. So wanted to set the stage here, right, with the kinds of equipment that we were dealing with so that we have something real to talk about, as we talk about these AI best practices. Now, given that this is a data science conference, right? Of course, I'm excited to share what kind of data that we use with you guys. So, in terms of the overall picture is that we pulled a lot of data, right? So each one of these data centers has thousands of sensors within it that measure various aspects of the cooling system. So with regards to the measurement of the environment, right, the state space, of course, you have things like the IT sensors, right, that measure, the power consumed, by the servers, right. You've got various, temperature and pressure sensors, right. You've got sensors that measure the flow rates, the pump speeds, the fan speeds, the external weather conditions, fault alarms, etc. Right. So these are sensors that measure the physical state of the plant. And then on the action side, so these are the things that our AI system is actually controlling, right? And on the action side, you've got decisions like which cooling towers and which chillers and which pumps should we be running? What are the temperature set points associated with these various pieces of equipment? What are the flow rates associated with them? What is the, percent, pump speed that we should run at? What's the RPM? What are the flow set points, etc. So from a big picture point of view, right, we've got lots and lots of sensors measuring different things with regards to the cooling plant. And we have, a bunch of actions, right, that our AI is responsible for that, these are the knobs and levers that our data center operators manipulate on a day-to-day basis, right? Which has an enormously large impact on both, the cooling, of course, of the data center, as well as the energy consumption itself. So to put this kind of together, right, the data that we just talked about is fed into an ensemble of neural networks. And these neural networks are responsible for predicting the temperature, the pressure, and the energy of the data center. Now, there are a couple of very important things to note here, right? Um, at any given point, there are billions of actions that you could take, right? And that's simply due to the permutational, complexity, right, of all the different actions available. So, if you, think back to the picture that I had just showed you, right? We saw a bunch of pumps, we saw a bunch of chillers and cooling towers outside, and heat exchangers and valves. All of them have actions associated with them, right? And these actions, the cumulative effect of all the actions. So the total possible actions that we could take, right, quickly explodes into the millions to billions, right? Due to the exponential increase. So what we do here is we take a snapshot of the current state of the data center of the industrial system, right, as measured by the thousands of physical sensors, and we concatenate that with the different actions that are available for evaluation, right? And for each one of these, for each one of these possible, combinations of actions, right, plus the state of the data center, we predict the future temperature, pressure, and energy consumption. Now, the second really important thing to note here is the emphasis on the word future. So one of the things that we discovered quite early on is that it's very, very important, right, to make sure that your system doesn't behave in a near-term, epsilon greedy kind of fashion. And we discovered that the hard way because in the early stages, when we quote unquote turned on our machine learning system, right, the AI program, calculated the optimal actions, and it came back to us and it said, "Aha, I've got it. In order to minimize the energy consumption, we need to turn everything off." And from strictly speaking, right, that's right. You could save a lot of energy by turning everything off. But of course, we know that in the longer term, right, that doesn't work because the effects of turning everything off will quickly result in future consequences, right, for the data center, namely in the form of melted servers, so that people can't get their cat videos anymore. So what we discovered here is that we actually want to force the AI agent to predict the future energy, temperature, and pressure of the system, right? So what I just described is the machine learning model, right, that predicts things for the data center. But the question, of course, is what do you do with this? So I'm going to take us through a high level of how this the system works. All of this is publicly available knowledge, right? We've actually tried to be fairly transparent with how the system works, and we've published a lot of info on this. So if you're interested, there are various blog posts out there and white papers that we've written on how this system works. But from a high level, the way that the system works is that every 5 minutes we have an AI agent that's based in GCP, because it's Google, of course, that pulls a snapshot of the data center cooling system, as represented by the thousands of sensors that we had just talked about. Now, it's important to note here, by the way, that for most industrial systems, right, the thousands of sensors, right, that data will be stored in either, a data historian of some sort, or, a building management system, a SCADA system, etc. So this information is then fed into the ensemble of deep neural networks, which I had just talked about. And the purpose of the neural networks, right, is to predict the future energy consumption, temperature, and pressure, right, as a result of the current state of the data center, plus all the different actions under consideration. And the reason why we use an ensemble instead of singular neural networks, of course, is to get a sense of the uncertainty in our predictions. So the control agent selects the actions that will satisfy the safety constraints. In this case, the safety constraints are the temperature and pressure, while minimizing the future energy consumption. So to make this very concrete, if you think back to the slide where I showed you, the diagram of the neural networks, right? You've got the current state of the data center, plus you've got a billion different actions that are under consideration. So what we do is we, for each one of those, billion combinations of, state space plus actions under consideration, we quickly predict the temperature and pressure, associated with that action. And 80% of those actions may violate the temperature and pressure constraints that were given to us by the data center operator. So we throw those out, right, because they violate the constraints. And then you're left with 200 million or so different actions, right, that still we predict that they will still respect the safety constraints. And of those 200 million actions, we simply select the set of actions that will minimize the future energy consumption of the system. And that optimal action, right, is then sent back to the data center, where the local building management system, or the BMS, will verify the actions against its own set of internal safety constraints prior to implementation. So what I've just described to you is a closed loop control system. We think it's a first of its kind, in the sense that this is an autonomous system. It's a cloud-based AI agent that autonomously controls this industrial facility and is running at many Google data centers now. This is one of my favorite graphs in the world because it provides such an easy to understand visual representation of the impact of what AI can do for these industrial systems. So these are real energy readings. So this is a holistic energy meter for the data center. And what you can very clearly see is that over this 12-hour time period when we were doing testing, right? So 12 hours is exactly one operator shift. You can very, very clearly see when we turned on the machine learning system, right, versus when we turned it off in the energy meter readings themselves. And in this particular graph, the difference is a couple megawatts of energy for the cooling system. This graph is quite possibly my favorite graph in the world. It's a little bit complex, so we'll break it down as to what's happening. So the green line over here is the AI system's performance with regards to the energy savings. So specifically, the green line measures how much energy we're saving relative to the historical baseline. And the blue line is a plot of how much data we've collected. So what's so interesting about this particular graph is that for this one data center where we turned on this autonomous AI control system, right? We start off with average savings of about 12%, but over the course of 9 months or so of continuous operation and learning and retraining, redeployment, etc., right? We actually ended up around 30% energy savings and is continuing to grow, right? The reason why this graph is so interesting to me is because I think this graph, more than any other I've seen, captures the essence of why the future of industrial controls is artificial intelligence, right? Rules and heuristic-based systems don't get better over time. In fact, these hard-coded rules and heuristics tend to be rather brittle, and the performance of these plants degrade over time, right? You literally have somebody or a lot of people come in, they figure out one way of operating the system out of millions of ways of operating, or potentially billions of ways of operating, and that is how the system will operate for the next 10 or 20 years. Whereas the kind of system we're talking about here, right, is a continuously learning adaptive system, right, where the value created by the AI actually increases over time, right? So and unlike traditional systems, right, which are either static or degrade in performance over time, an AI-based control system can actually increase its performance over time. So this is one of the main reasons why my co-founders and I were super excited to start a company, because we wanted to help other people, particularly within the industrial sector, achieve this kind of performance, right, for their own AI applications. So that's kind of the context for a real world example that of an AI system that we've applied. Now, the more interesting thing, of course, is what did we learn from this process and many of the other areas where we've applied AI. So the next section here is really about lessons from the field, right? On best practices for how to make AI work in the real world. So when I reflect back on our experiences, I think the single biggest lesson I've learned is that the simplest AI is usually the best AI. Right. And you don't need, deep mind level complexity. You don't need hyper advanced algorithms. Like a lot of the low hanging fruit can be gotten with very simple AI systems, like the one I just showed you, actually, right? Like literally, the AI system that I showed you, right, for predicting, future energy consumption, temperature, and pressure. That's a fully connected MLP that is honestly fairly easy to implement, right? The real innovation is not on how advanced the AI algorithms are, but rather how do you integrate these AI systems with real world infrastructure, right? It's the integration piece, that's the hard part, not the AI. So really what I would note here is that, we talked about how industrial systems are highly complex. Well, even simple neural networks, a simple two hidden layer neural network can capture, really, really complex mathematical functions and intense nonlinearities, right? Um, I would note here that complex AI systems are extremely difficult to debug because you don't know what the heck is going on, right? They are, of course, very expensive to train as they become more and more complex, and also they're more prone to failure, right? Because you're introducing additional points of failure, right? Simple systems are more robust; they have less points of failure. They're easy to understand. So overall, we in our experience, simpler AI systems are just better, right? There's also an important point around trust, right? Because complex systems tend to be difficult to understand, right? It makes it very difficult to verify the learnings of the AI systems, verify that it's learned the right physics, right? To provide explainability in the context of the decisions that the AI agent is making, and so on. And in fact, we'll actually have an entire section shortly on how to turn black box systems into more gray box systems to increase trust. So, I would summarize here as try to, if the goal is to productionize your AI system, so actually get it out into the field to have real world impact, then we should strive to both reduce the model complexity, right, as well as reduce the number of features and actions to the absolute minimum necessary in order to achieve the things that you care about. And of course, there are many, many ways that are beyond the scope of today's conversation around like how you select the right features and how you select the right actions, right, to the minimum necessary in order to achieve your objectives. The second lesson learned is really around data quality. So I think, since all of us are at this Kaggle data science conference, we all know that data quality trumps data quantity. The question that I'm really interested in answering is, what does good data quality mean in the context of AI for physical infrastructure? So I thought, one of the more useful ways is maybe by starting first, to talk about what are the common ways we've seen, after applying AI dozens of times to various physical systems, around like how does data break in the real world. So, these are some general buckets for the most common ways that we see, data quote unquote breaking, right? Of course, missing sensorization is very high on the list, right? We also see a lot of misnamed data where, it's not intuitively obvious what the data is you're looking at, right? Especially because the naming conventions associated with the sensor data, if it's stored in like a data historian or in some other database, right? It can, it can be quite difficult to interpret, what the data actually represents. Of course, we get a lot of problems around low variance data, and this is actually tied to the fact that most physical infrastructures, like most physical systems, are hard coded, right? And the effect of them being hard coded means that they've spent most of their lives operating within very narrow operating regimes, right? So we often get quite low variance data, which of course makes it difficult, right, to extrapolate and generalize learnings. We see quite a lot of sensor drift, right? Because sensors haven't been calibrated in a while, or sometimes you see a lot of stuck sensors where either the sensor itself has broken or there's some error associated with the sensor, so that they're just reporting repeating values. And I would say the last most common way that we've seen data quote unquote breaking in the real world is that the underlying system itself has changed, right? So the historical data that you've collected is not actually representative of the system today, because maybe some equipment got swapped out, maybe there was some maintenance performed, right? So all of a sudden the equipment performance has improved because they cleaned the heat exchanger, or they swapped out the ball bearings in a pump, a lot, something like that. So those are some common ways that data can break, right? When you're talking about AI for physical infrastructure. The interesting question, of course, then is, what do you do about it, right? Like, there's so much bad data out there, right? Like, what should we do, to turn this bad data into good data, right? For machine learning. Um, we think that the best thing to do is to conduct a gap analysis. So, a gap analysis essentially answers the question of what is the current state of the system, so a data health audit, if you will, versus where you need to be. So, in order to implement this AI project that you're thinking of, what is the current state of the system, your starting point, versus where you need to be? And that's the gap that we need to overcome, right? So this is where we would then work with our customers to implement a quote unquote AI readiness plan, right? But it's essentially a series of steps that addresses the gap, right? And I would also note here that this is also a really good time to conduct some guided exploration that's needed to generate the either missing data or areas where we don't have a whole lot of variance in the operational data. So that's kind of a broad point, right? But really, what I would summarize this as, there's no such thing as perfect data, right? Like I outlined a couple of ways that data can break, but honestly, there's 100 other ways that your data can break, right? There is no such thing as good data for physical infrastructure. So really, in our experience, the key here is to embrace the fact that there's no such thing as good data, and to engage with the customers quite early on, right, to shape their quote unquote their data journey, right? Most of these large industrial companies, or these physical facilities, right, they are still in the early stages, right, of recognizing what you can do with data, what good data hygiene means, etc. This is really the perfect opportunity to kind of engage for the long term, right? Where you embed with these folks early on, right? You help them craft what an AI readiness plan, or really, I guess we could broaden it to an advanced data analytics kind of plan looks like, right? To help them, become AI and data ready in the future. So the third lesson that I wanted to share with you is hopefully aptly summarizes safety is king. So the point that I want to make here is that performance is irrelevant if it compromises safety, right? It doesn't matter how good your AI is if it compromises, safety or the continuity of operations in any way, right? And the rationale for this is obvious, right? Most physical systems are incredibly expensive pieces of hardware, right, that involve the risk of human safety as well, right? So whether you're talking about a chemical manufacturing facility, which often costs from $1 billion to $10 billion worth of capital machinery, right? To a data center which has hundreds of millions to billions of dollars of servers inside of it, to maybe a food and beverage factory, right? Which of course has a lot of safety implications as well, right? If you're talking about implementing AI in the real world, in these large industrial systems, it means that there's no room for error. So the question here is, given that safety is king, what do we do about this? So the most hopefully helpful advice that we can give here is to embrace a concept actually from taken from network security, specifically zero trust networks. So this is an interesting analogy because with modern IT networks, right? Modern IT networks have moved away from the idea of kind of defending the periphery, if you will, right? So putting all your defenses, at the edge of the fort, and if a bad guy comes in, right, then everything inside the fort is kind of screwed, right? So modern IT networks have moved away from this to to focus more on resiliency, and it's the same concept that we've adopted here. So very concretely, instead of putting all your efforts into foolproofing your AI system, right? Our suggestion is to improve more on resiliency. How can you automatically detect and recover from bad situations? And this is really based upon the acknowledgement that there will be mistakes, right? Because there are simply too many edge cases that you have to consider that are not represented by the data, right? So very concretely here, it's very easy to go from 90% to 99%, but it's significantly harder and way more expensive to go from 99% to 99.9%, right? Which is the requirement in most of these industrial systems, right? You need anywhere from 3 to 5 nines of availability and reliability, right? This is, I think, best exemplified in self-driving cars, right? Where the entire industry for self-driving cars has been stuck, going from 99% to 99.9% for the last few years. This is an incredibly difficult problem to solve. So our suggestion here is borrowed from network security, right? To assume from day one that the AI system will fail, and then to build in the necessary fail safes and recovery mechanisms so that when something bad happens, you're able to quickly detect it and to quickly recover from that situation without compromising the underlying system's safety. So here is a schematic, of best practices that we developed during our time at DeepMind that have been implemented in Google's data centers. And of course, all of this material is public domain knowledge, so we've provided links at the bottom, right? But if you just Google, Google data centers, plus DeepMind, right, you'll be able to find all this information. So there are some very obvious best practices like continuous monitoring, right? Like everyone knows that you should do continuous monitoring, right? To make sure that the AI is respecting the safety constraints that you've outlined. There are more nuanced and advanced safety measures, right, that you can put in place. So the ones that I want to highlight here are, the automatic failover and smooth transfer. So the idea here is that you shouldn't have to wait for a human operator to notice that something is wrong and to take manual control. The AI, because it's monitoring itself, should be able to automatically detect when something is wrong. And if something does go wrong, it should be able to bumplessly transfer itself back to the underlying, rules and heuristics or some kind of a safe operation mode, right? Without requiring human intervention, right? It is a completely automated system. Right. There's, there are other best practices like two-layer verification. So not, the AI should of course, check for any kind of safety constraint violations on its side, right? But you should also check on the local system side as well, right? So build in an additional layer of checks, at the SCADA level or at the building management system level, right? Before actions are implemented. Of course, in our experience, the information associated with uncertainty, right, of AI decision making is incredibly helpful. So, suppose that you get an action that we think it's going to save a lot of energy in the future, but we're only 80% confident that it's the right decision. Well, maybe you don't actually want to take that action because the confidence interval is not high enough, right? So maybe we only want to implement actions that we're 99% confident is a good action, right? Where good is defined by not violating safety constraints and minimizing the objective function, right? So the information associated with uncertainty can be tremendously useful in this case, right? Um, and of course, at any given point, right, you have the capability for human override. So even though this is a fully automated system, right, we literally have a digital big red button, right, that operators can push if they ever feel like they want to take control of the plant back into manual operations, right, for whatever reason. So these are just some best practices, right, around how you implement AI safely for these mission critical systems. And again, right, I can't stress enough the point that, you know, even simple AI methods can get enormously large gains, as evidenced by the fact that we got 40% energy savings in Google's data centers, which were highly optimized to begin with already, right? Because we've literally spent, 10, 15 years optimizing these large systems, right? The real innovation is how do you bring this technology to make real impact, right? In live production, right? How do you productionize the technology, which really becomes a question of how do you integrate with the underlying systems in a safe fashion. So, lesson number 4 here is, is summarized as trust is not blind. So, what we mean by this is that, of course, changing human behavior is incredibly hard, right? It's difficult to get people to adopt your AI system, right? So, building trust, right, is really essential, right, component of getting folks to adopt that AI system. So really, this section is meant to expound upon some different ways that we've learned from doing this many times, right? On how do you build human trust in your system so that you can deploy it and make large performance improvements, right? So there's really 2 buckets of thought here. The first bucket is to make these systems more transparent. So nobody trusts black box systems. Literally, the single most common feedback that I get from talking with various customers is, why should we trust your black box AI systems? So really, the suggestion here is to turn the black box into more of a gray box or maybe an opaque box. I don't think we'll ever get, to a white box. AI is simply, not that at that stage yet, although there's a lot of good work going into AI explainability and verification, right? But I think given the limits of today's technology, the best we can do is turn it into a gray box. And there are some very, concrete ways we've discovered that seems to really resonate with folks in the field. So we've outlined for them below. The first one is quite simple. You can simply show what the predicted gain is versus the current state of the system if the operator or the control system were to implement the actions, right? Another very simple method is to conduct some sensitivity analysis. So this is literally where you freeze a bunch of variables, right, and you manipulate one variable at a time, and you look at the effect on the overall system level performance, right, as you vary these single variables. And the intent of these sensitivity analyses, right, is to provide kind of a check, an easy way to verify the physics, right, of these AI models to ensure that it's kind of learned the right thing. Um, Another very simple tactic, right, is to show the expected trajectory of the system. This is particularly true if you have some sort of model predictive control, where it's very simple, right, to display what the expected trajectory of the plant is, given what the AI system is doing now. And moreover, right, it makes the human operators feel significantly more comfortable, right, giving them that visibility into where the system is headed. And then, of course, we've already talked about confidence intervals, right? And how, showing the confidence intervals can really, increase, trust, right, in the overall system. The second large bucket of thought here is really around involving the customer and the domain experts early on, right? So, there's a very general observation that I think is true for pretty much everybody, right? Which is nobody likes being forced to adopt something that they didn't have a say in. So, our suggestion here is to really increase buy-in by engaging your customers, right, and their domain experts really early on. And of course, this is really helpful for the folks who are building the AI system as well, right? Because the customer's domain knowledge is extremely vital to the overall success of the AI project. And that actually is the final lessons learned, right? That I wanted to share with you guys today. The fifth and final lessons learned here is to not underestimate the importance of domain expertise. In all of our experience applying AI to date, domain expertise has consistently been the single largest driver of AI success, even more so than how advanced the AI algorithms are or how much data you have, which sounds a little bit heretical to say this at a data science conference, right? But in our experience, domain expertise is by far and away the number one predictor of AI success. The reason why this is true is actually fairly obvious. So we all know that AI is an incredibly powerful technology, but we also know that AI is a very narrow technology. There's no such thing as out of the box AI yet, right? And AI, we also know, is not good at generalizing, right? We're at the stage where, an AI that's trained on one data center can't even, be copied and pasted over to another data center, right? Or, an AI that's trained on a Ford, can't be applied to an AI that's trained on a Chrysler, right? So AI is very, very powerful, but it's also extremely narrow. And as a result of the limitations of the technology, every AI solution needs to be tailored to the unique application, right? Now, who actually understands the application, the domain best? It's the customer and their domain experts, right? These are the kind of folks, who have worked in a particular plant, a particular company or particular industry for the last, 10, 20, 30 plus years, right? Because they have spent so long understanding these these domains, right, they can understand the facility in ways that cannot be measured by data but yet are incredibly important. And we often call this intuition, right? But these are the folks whom, as they're walking across a plant, maybe they'll hear some strange noise, right, and they immediately know, oh, that chiller or that condenser water pump, it needs to have its ball bearings changed, right? That's the kind of thing that can only be gained through many years of hands-on experience. And the final thing that I will note here is that this knowledge is critical, right, for defining the AI problem. So the domain experts are pretty much the only ones who can, help you, select the right objective functions, right? They can help you select what the right actions are, what are the, constraints associated with those actions. They can give you a lot of, insider knowledge on which features are the most important, right? For your AI model, etc. So really, this slide can be summarized as domain experts are the folks who understand the application and the facility the best. So, it benefits everyone if you involve the domain experts very early on, right, in the delivery of this AI system. So those are actually all the lessons that I wanted to share with you today, right? The final thought here is really just kind of sharing like what it is that Phaedra believes in, right? So we left we left our previous companies because we experienced firsthand just how incredibly powerful AI is, but we also saw how exclusive AI can be, right? The benefits of AI, right, are currently limited to very few companies in the world that have the resources, the talent, and the scale to commercialize it, right? And I think all of us at this conference, right, this is something that will be deeply familiar to all of us. So Phaedra's mission is to make AI more accessible. And we do this by helping the domain experts, whom we just talked about as having the most knowledge and understanding of these industrial systems. We help domain experts develop AI solutions via low code, no code software. Right. So it doesn't matter if you don't know TensorFlow, if you don't know what DQN is, right? If you don't know how to spin up a virtual machine or set up Jupyter notebooks, right? All of that doesn't matter because we can take care of that for you so that you can focus on using your domain expertise, right, to develop, very complex, high impact AI solutions that no one else can. So if this is something that sounds interesting to you, or if you have any other questions, comments, thoughts about this presentation, right, definitely encourage you to reach out. I've provided my personal contact as well as our website for our startup below. And I hope you enjoyed this presentation. It's been a genuine pleasure sharing this information with you all. And I hope that it helps you, as you apply AI to real world infrastructure. Thanks and have an awesome day.